Okay, chapter 4, section 1 is all about triangles, and specifically, we're going to talk about applying the triangle sum properties. So remember that the word sum has to deal with addition, so whatever we're talking about today is going to have to do with adding certain things together. All right, so when we talk about a triangle is very much like a triangle that you've always understood. It's a figure formed by three segments, bless you. Notice three segments, all the three different lines, joining three non-collinear points. I think you would agree that these 3 points here in this triangle are non-collinear. While two of them may be on any given line segment, all three are not on the same line. The point where those segments meet at A, B, and C, that's a vertex. And if we talked about all of them again, those are the vertices. And when we talk about those segments, in terms of a triangle, we're going to talk about the sides. Even though they are line segments, those line segments make up the sides of these triangles. For example, when we refer to a triangle, we do not use the angle symbol. We just draw a little triangle in front. So if I'm referring to this, like let's say I was doing a proof involving a triangle, I might, call this triangle A, B, C. But notice I drew a little triangle in front. That tells me that what I'm talking about is not an angle, it's a triangle that I'm talking about. If I said an angle, then I would be talking about specifically one of those angles of the triangle. But putting that in front says, hey, whatever I'm about to say is talking about triangle ABC. The vertices we would just list as A, B, and C. They are just points where two segments meet. And if we were to look at the sides, now you can reverse any of these letters too. The order doesn't matter. We can call them AB, which is here. There's one side. Line segment BC, or side BC. And line segment CA, or side CA. And at those vertices, we have three angles. So shapes with three sides will have three angles. So we've got angle A up here, angle B down here, and angle C right there. Three angles. I mean, it's called a triangle, right? Three angles. That's its whole thing. That's why we call it a triangle. It is made up of, we could call it a tri-side, but that's not as interesting. Whoa, just blew your mind there, right? All right, triangle, three angles. And made up of sides, and we have angles as well in there, and those are the things that we're going to talk about. Those angles in there are the most important thing that we're going to talk about today. They have a very special relationship in every single triangle in the world. So we're going to talk about some different things. Now please, I'm going to tell you right now where the biggest problem is going to happen on the next quiz and test. I'm going to tell you right now, so this is the part you want to pay attention to. This word classify, when we classify something or we're doing classification, it just means to name something. That's all we're going to do, is we're going to name something. If I ask you to classify something, or what is something's classification, even in science, we're talking about its name. So we are about to name these triangles by their sides. In a moment, we're also going to name them by their angles, but right now, all we're doing is giving it a name based on looking at the sides. So I'm taking a moment for that because I'm telling you right now, I've done this enough that where does the mistake happen? Somebody doesn't know what classification means and they start writing a whole bunch of different words and formulas. When it says classified, it just means name it. So you've run into these before. You've definitely heard of a scalene triangle. These are things that I know just because I've got a little one in elementary school and he's learning these same things. So a scalene triangle has no sides that are same. All three sides are completely different numbers. None of the sides are equal to each other. Whereas isosceles has at least two sides that are the same. So notice here, you have these congruency symbols. That means that this is an isosceles triangle. Now, it said at least two sides. So actually, this one down here is an isosceles triangle as well, but we're not going to call it an isosceles triangle, and I'll tell you why. It's like, in just a moment, we're going to see something, I'll be like, why do I not call that one isosceles, since it has at least two sides that are same? Because we get into a more specific one, whereas we have an equilateral triangle. So we have a scalene triangle, an isosceles triangle, and an equilateral triangle. An equilateral triangle has all the sides are the same. 1, 2, 3. Now here's why we have that at least part. When we talk about isosceles triangles, there's going to be some rules that I tell you. When you see an isosceles triangle, you are allowed to, bless you, you are allowed to do this. So then you're going to find out these rules for isosceles triangles. It's going to apply to these, but it'll also apply to those as well, because equilateral triangles are also isosceles triangles. It's like every square in the world is also a rectangle, right? Because every square meets the properties of a rectangle. It has two sets of opposite sides that are all congruent. All, like, the left side and the right side are congruent to each other. The top and the bottom are congruent to each other. It's got right angles just like a rectangle does. But a square is a more precise version of it has like even more categories, more specific things that it needs to be a square. Just like an equilateral needs a more specific category to be equilateral. So, scalene, no congruent sides. Isosceles, at least 2 congruent sides. And then equilateral, 3 congruent sides. Now notice, these were names based on the sides, because I'm going to be naming something in a minute based on their angles. So now we are going to classify by the angles. Now we're going to name, like, triangles. Again, let me just put that this means name them by their angles. We're going to name them based on their angles. So we've got 4 kinds of triangles that we can classify by their angles. First of all, there is acute, where make sure this is very important, all the angles have to be less than 90 degrees. Like that word acute, like, right? Those are the tiny angles, like the small angles. All of them are less than 90 degrees, every single one of them. We have an obtuse triangle where you will have one angle that is greater than 90 degrees. So one of the angles in there will be greater than 90 degrees. You can't have more than one angle in a triangle that is greater than 90 degrees, and we'll talk about that why in a minute. But right now, just know there can only, if it has an angle that is greater than 90 degrees, then that's the only one in there. There can't be another one. We've got a right triangle, and a right triangle has one angle that equals 90 degrees. You can't have 2 angles in a triangle that equal 90 degrees. You can only have one, and we'll talk about why in a little bit. So obtuse and rights, you can only have one of them. One obtuse angle, one right angle. And equiangular means that all the angles are equal. Every single angle that in there is exactly the same. So notice acute, that we've got inside the acute triangle here. We've got 3 angles, and you can see that every one of them is less than 90 degrees. You can see we know what 90 degrees looks like, and that's less than 90 degrees. So this is definitely acute. A right triangle I can identify by this right there. If you do not see that, do not assume it. If that little red box weren't there, we could not assume that this was a right triangle. We have an obtuse triangle. I can see that right here, there is an obtuse angle. That is definitely greater than 90 degrees. I can see it's open more than 90 degrees. And then finally, an equiangular triangle where all the angles are exactly the same. 3 congruent angles, all of them. Yes, ma'am?
Is it possible to have an equiangular triangle that isn't equilateral?
Is it? That is a great question. Can I answer it in a minute? So her question is it possible to have an equiangular triangle that isn't equilateral? And actually, you just stumbled on something kind of amazing about triangles, and we'll get to it in just a minute. So if I can just put pause on that for a minute. Okay, probably one of the biggest things that you're going to learn in geometry right here. This is something you will use every single day for the rest of the time in geometry. This will always happen 100% of the time. This is called the triangle sum theorem. And it says that the sum of the measures of the interior angles of a triangle is 180 degrees. It means that 100% of the time, every single time in a triangle, if you were to take angle A plus angle B plus angle C, whatever they are, it will 100% of the time always equal 180 degrees when we add them together. A plus B plus C equals 180 degrees. So let's see something here. Let me draw a right triangle here. And I'm going to put 90 degrees there. And I'm going to put 60 degrees there. What would that last angle be based on this information? Why?
Because I added 90 and 60. And then I did 180 minus 150.
means that has to be 30 degrees. So this is why this is useful to us. If I have a missing angle in a triangle, if I have 2 out of 3 angles, it's so super useful for me to find them. I go, oh, well, I know them, and I go, oh, okay. I can find that third one based on only having 2 angles. Okay, exterior angle theorem. The measure of an exterior angle. Now, when we talk about exterior and interior angles are inside the triangle. An exterior angle is an angle that is outside the triangle. So we've got this triangle right here. The measure of an exterior angle of a triangle equals the sum of the measures of the 2 remote non-adjacent interior angles. So what they're saying is that this angle, angle C over here, or angle 1, whatever, sorry, I can't call it angle C. I can call it BCA or angle 1. That angle right there is equal to these 2 things added together. This angle here plus this one here. So let's say that I've got, let me try to put together an example like this. All right, let's take a look at this. Let's say that I want to find out the measure of angle 1, which is this angle right there. How could I do that?
120 plus 20.
Which is equal to? 140. Those 2 together will always be equal to this. And let me show you why. You can either just believe that and go, you know what, he told me it, so I'm going to believe it. But I can also show you why this makes sense. Let's ignore angle 1 for just a minute. Let's pretend that angle 1 isn't even there. I'm going to draw it, but let's pretend it. Now, we knew that this is 120, and we know that this is 20. Let's talk about angle 2. Let's forget about angle 1, ignore angle 1, pretend it doesn't even exist for a minute, but let's talk about angle 2, that third angle inside this triangle. What would it be?
It's like not vertical.
I'm actually talking about the number. I want to know what is the measure of angle 2. Yes, sir?
40.
How'd you get 40 degrees?
Well, because it has to add up to 180, so.
Okay, so 120 plus 20 would give me 140. And if I were to subtract that from 180, 140 gives me 40 degrees. Okay, so why is that showing us anything about the exterior angle? Well, you got something, Colette?
Because they're linear pair.
They are a linear pair, which means that this would have to be 140. So really what we've got is that if this one on the outside there is forced to be, remember that we go, it's forced to be what those 2 things added together were. There's no other way, because what we had to do was add these 2 things together and subtract it from 180 to get this, and then we subtracted the 180 minus that to get back to 140. So it'll always be the case that we call these 2 the remote interior. Remote, when something is a remote, like a remote location, it's far away. So it means the ones that are right, not the 2 angles that are right next door, but the ones that are the furthest away from that one. Those are the 2 angles that you need to add together to get that exterior angle. Okay, so let's see another situation. What about how's that going to help me find angle 1? Yes, ma'am.
You do 125 minus 35.
Okay, so we get 125. Let me just show this another way. You're not wrong. So here's we go. We know that these 2 angles, when added together, so the measure of angle 1 plus 35 is equal to 125. And what she's saying is subtract 35 from 125. Which leaves me with what? How much? I think you're right. I just couldn't hear you. Did you say it? I just didn't hear.
Yeah, 90.
Oh, 90. I'm sorry. So let's say that I wanted to now. Let's say that I now know that the measure of angle 1 is 90. This is 90 degrees up here. How much is that third angle in the corner?
180 minus 125.
Okay. $55 degrees. So we've got a triangle here that has 90, 35, and 55. What kind of triangle is that if we classify it by its angles? It's a right triangle because it's got 90 degrees up there. So just by using that exterior angle there and the two remote interior angles, I was able to classify it by its angles. Okay, so a corollary to a theorem is a statement that can be proved easily using the theorem. So this is where you guys get to see all of my dorkdom. When I talk about corollaries, what we're talking about here is it's like the DLC of the math world. Like you get these theorems, we give you these theorems, and they're like, hey, remember that thing I told you about this? Here's a little extra thing that adds on to that. So corollaries are like just adds on to things that we already know. So one of the corollaries we're going to learn is a corollary to the triangle sum theorem. So we already know that the three angles in a triangle are going to add up to 180. Here's a corollary to that triangle thing. Here's a little added thing that you can add on to that is in that same area there. So it says that the acute angles of a right triangle, are complementary, meaning that a measure of angle A plus the measure of angle B is equal to 90 degrees. Here's why that should make complete sense. How many degrees are in every single triangle in the world?
180.
How many degrees are accounted for right there?
90.
That's 90 of them. How many are left for A and B?
90.
There has to be 90, which means that I don't care which one is which. They both have two different numbers, whatever. But when they add up, they have to equal 90 degrees, meaning in a right triangle, A and B, the two acute angles, will always be complementary. They always will be. There's no other choice because there's 90 degrees left over for them to split up, however they want to split it. All right. State whether the triangle with two angles having the given measure is acute, right, or obtuse. Talk to me about why it would be a terrible idea to classify these triangles based on only two angles. Because what? So why would the third one matter? Like if I see right there, look, I see 55 and 43, those are both acute angles, so why can't I just call it acute? What if the third one is a right angle? What if the third one was an obtuse angle? These are all things that we have to look at here and go, okay, well, what is it? Look at D. My first opinion on D is oh, you know what? That's probably equal angular. Because look, two of them are the same. But we're going to see that different things happen based on them. So let's talk about what should we do for A to classify this. Yes, ma'am.
You add,
Oh, that's okay. Sorry, I should have been clear.
I subtracted 55 from 13, and you get, from 43, and then you get...
Why 55 from 43? Why would we subtract those two numbers? First of all, wait, let's do this. Okay, let's add them. So we've got 55 plus 43, which gives me 98.
And then from there,
How many degrees in total are there?
there's 90.
In every triangle in the world? 180. So you've already counted for 98 of them. So what should I do with that 98? Subtract it. What does that leave me with? How much? I heard three different answers. I heard 62, 72, and 82.
wait, it's 82.
Let's take a minute. Just check your subtraction.
Just kidding.
Okay, so we've got 82 degrees. What kind of triangle has angles of 55, 43, and 82? It is acute, but I didn't know that until I knew that third angle. Without that third angle, I couldn't make that assumption. 47, 43, how am I going to find that? Let's add them together. 47 plus 43, 90. So if I've got 90 of this triangle, how much is left for the other angle? 90. So what kind of triangle is this? It's right. Now I'm classifying it only by the angles, not by the sides. Next up, we've got 80 plus 75 is 155. And 155, 180 minus 155 leaves me with? So what kind of triangle is this?
Acute.
It's acute as well. 33 and 33. Remember, this is the one that I made a prediction. I said, well, look, two of the angles are the same. This is probably going to be a equal angular triangle. And we get 6, 6. If this is 66, how do I figure out the last angle? 180 minus 66, which leaves me with 114. This is not, in fact, an equal angular triangle. It is what kind of triangle? It is obtuse. So don't fall into that trap of trying to use two just because they're the same. It is a trap. 24 plus 66, which gives me 90, leaving me 90. This is a right triangle. Yes, ma'am.
For equiangular triangles, is there only one possible thing?
Yes, talk to me about what you just stumbled upon there. She just said, for an equal angular triangle, is there only one possibility that they could be? Yes, but explain that to me. Why? How did you come across? She's saying this, that if I tell her that I have an equal angular triangle, she says, I already know all three angles. I could tell you all three of them, just based on what I said. It has to be 60, because think about it here. If there is 180 degrees in a triangle, and each of these are exactly the same, well, that's 180 divided by 3, and 180 divided by 3 is 60, 60, and 60. All right, we need to find the measure of angle A in every scenario. Now, angle A is changing here, so we are going to find every single one. Yes, ma'am. Yep.
The left triangle
Okay.
has to equal to 180, so the last angle has to be 50. It's 50. That's 50.
Okay, she's saying that this has to be 50 because 50 plus 50 is 100, and 100 plus 80 is 180.
And then vertical angles,
Beautiful. Check this out. Vertical angles right there.
so the other one would be 50, and then A would be 80 because 50 plus 50 is 100.
Have to be. Yes, sir.
Could you just use the alternate interior angles just to figure that out?
Where did it say that they were parallel?
Oh, snap.
That's what we have to be careful. I'm going to tell you right now, like the proofs were hit or miss for people because they started doing that same thing. They were like, well, they're parallel. I'll be like, if I didn't say they were parallel, you can't go with that. What's that?
No, because you said, well, I don't, how are they alternate interior angles?
He said, couldn't I? He's looking at this. So let's pretend they were parallel for a minute. Actually, to be honest, now that the triangles are finished, I can guarantee to you that they are parallel, and I'll show you why. I can prove to you that these are parallel, but I can only prove that because of what they both said. Audrey completed the triangle for me, and now I can see the angles there. And so what I can see is this. I've got 80 and 80 right there, right? Now notice this. Let's pretend that I just pay attention to those gray lines and this transversal here. Block everything out in your mind. Then there are these interior area. Here's this interior area all in here. And that interior area has two alternate interior angles that are congruent. Therefore, they would have to be parallel. But that's not how we did it. What we did was we started from the left triangle, and there was that angle that's on the right-hand side missing. So we said, well, let's add up 80 and 50, which gave me 130, knowing that the last angle would have to be 50. We expanded from there and said, well, look, vertical angles right there on the other side, and kept making our way all around. Well, 50, 50, and then 80 would be the last one right there. So this is very much like a puzzle of like, what do I see? What do I know? What can I use?
Oh, I thought he was talking about the 50s. I was trying to figure out how those were alternate.
No. It's the 80s that would be. Actually, the 50s can be as well. Like it's just a different transversal. So then we would use this transversal, and then these two are alternate. But it depends which transversal we're using. It changes depending on the alternate interior angles will change depending on them. Somebody different. You want this one? Oh, you had a question about this.
So like, say you were to give us a question like that, but like, would you like ever like classify it as parallel, or would you just be like?
If let's say that I gave you this as a proof, by the end of this chapter, no problem, you would be able to do this as a proof, proving me that lines, I don't know, A, B, and C, D are parallel. Like I could turn that into a proof right now. Like you guys may not be ready for that right now, but that would definitely be a proof. What you just did there by finding.
Is Natalia Herrera just to class?
Yes, I think I marked the wrong student then. Give me 1 second. I'll tell you right now. Sorry.
Okay.
Yeah, it's Sophia Herrera who's not here. I'm sorry.
Okay, thank you.
Thank you.
Wait, so if you want to turn that into a proof and like ask.
Let's not jump to proofs yet because you're talking about the end of this lesson where I'm just showing that this is where this is going. Like we've got a lot of the key pieces where you can see it, but I'm not ready to say, now here's your proof on it. Yeah.
The thing is, I don't understand how the lines are parallel. It's like
Don't worry, that's not what we were doing there. He just brought that up. Like he just said, could I do this? So let's not go there yet. That's not what we're trying to do. We're not trying to talk about parallel yet. All we're talking about is finding these angles. That's all we're doing.
yeah, but how do you find the angle if you're not parallel?
Okay, so let me go back then. This is what we did. Let me erase this. Okay, let's look at this triangle right here. Let's do this, the faster version here. Let's look at that triangle right there. What is the missing angle? How did you know that?
Because you add 80 and 50 and subtract it.
And you got 50. Focus in on this area right here. What can I do directly across from that 50? Over here. What can I put right there? Like I'm focusing in that circle there.
Oh, 50.
Another 50 because that's vertical angles right there. Now I've got on the right hand side I've got 50 and 50. What's the last angle? 80. It had to be. All right, let's move on to this one. Somebody new, talk to me. Yes, ma'am.
You're going to go in the bottom triangle and do 60 plus 40
Okay.
equals 100. And then 180 minus 100 equals 80. So that's that measure the angle. And then on the other one, that's congruent. So automatically the other angle is going to be 80. And you're going to do 80 plus 40, which is 120.
Okay.
And then 180 minus 120 equals 60 degrees.
Perfect. Okay. Somebody different. Hook me up with this one.
Alright, so on the right, you add 110 and 130, and that's 130. Then 180 minus 140 is 40 up there. Then you do it, so on the other side is 40. Then 40 plus 30 is 70. 180 minus 70 is 110.
So using even two different triangles, we were able to pull them together and find all the angles there. That's all the things that we can do. We're going to be able to do a lot more with that, but this is where we start going. This is something you are literally going to use all the time, like everything, all the time. Triangles are probably the biggest part of geometry. Like, that's all anybody remembers is all these weird things about triangles you had to do. All right, let's find the measure of angle A. So remember, angle A is this one right here. Somebody hook me up. Yes, ma'am.
It'd be 40 degrees because it's like the remote to 120.
Okay, so the exterior angle is equal to the sum of the two remote interior ones.
And then that'd be 40 because he was 40.
Okay, and let's pretend we had really ugly numbers there. You should get in the habit of doing 120 is equal to 80 plus something. You should get in that habit because what if those were decimals in there? You may not be, like, we can all quickly see in our head that that would be 40. Like, that's it. But what if they were really ugly numbers with fractions and decimals and things like that? Then just get into the habit of going, okay, I just need to set this up, in which case subtract 80 from both sides, and we could see that x is equal to 40. Yes, sir?
Can you also do 180 minus 120, or do you want us to do it?
You could do 180 minus 120, but that would give you this angle right here.
Yeah, and you define
And then you'd have to add 80 and 160 and then find the last one, which would still be 40. I feel like that's a little more work, but yes, it's another way that you can get there. Huh?
Can I do E?
Yeah, take E.
Okay, so it says that angle G is equal to 100.
Notice that I'm going to write 100 here. You know why I'm going to write 100? Because you know what is a huge mistake somebody might make on this one? Let's take away the 100 for a minute. What might somebody assume by looking at this? That it's a right angle. It looks like a right angle. I'm not going to lie. Whoever even drew this probably drew it pretty inaccurately because that is 100 and that totally looks like 90, but they said it was 100. So I'm going to put in 100. No, I'm sorry. Go ahead.
And then it says that angle FEH, so like the exterior angle,
Okay.
is equal to 3 times angle F. So, but angle F can just be represented as X.
Okay.
So then,
Do you see what you did there? It said that FEH, the exterior angle, is equal to 3 times the measure of angle F. So I just wrote that there.
So would angle FEH be 3x?
yeah.
FEH? Yeah, exactly. Yeah.
So then, if you go back to the exterior angle theorem, it says that the sum of, like, basically what it says that the sum of, like, the farthest two angles
The two remote interior angles.
are equal to the exterior angle.
Good. So x plus 100
Is equal to 3x.
is equal to 3x because it's 3 of the measure of angle F, and angle F is, we called it x.
So then what you do, you have to get x on one side, so you can so to make it easy, you subtract x from that side, you subtract x from both sides, and you get 100 is equal to 2x. And then you solve accordingly, so you divide it by 2 on both sides, and then you get x is equal to 50.
Okay, so this angle up here is 50 degrees. What is the exterior angle out there?
150.
That's 150 out here. What is that angle what is angle FEG?
It would be 30.
30, because it has to equal 180 in there. If I had to classify this by its angles, what would I call this triangle? An obtuse triangle. So it's an obtuse triangle. We used all that information there. Now remember, like, in your homework, it's going to ask you about sides too, but the sides are a little easier to deal with. You just look at the numbers and go, okay, which one? Like, be real careful, because here's the other thing people try to do. People try to say all the sides of a triangle equal 180. That is not true. Think about it. A triangle could be as big or as small as possible. Like, there is a very important triangle that we're going to learn about in this class, and it looks like this. 3, 4, 5. It's called a 3, 4, 5 right triangle. It's so super important, but that doesn't add up to 180. The sides don't add up to 180. The angles do. So be very careful. Huge mistake you can make. Don't worry about this right now. It's only the angles that have to add up to 180. That's all we got. I'll tell you what. I'm so glad you brought it up. So her question was, and we're going to learn this in later lessons. She said her question was, she had an equal angular triangle. We were looking at this, equal angular. And her question was, is every equal angular triangle also equilateral? And the answer is yes. Every single time, 100% of the time, it will happen. sorry. It will also be true the opposite way, is that if you see an equilateral triangle, 1, 2, 3, it will also be equiangular. So it works both ways. If you see an equiangular triangle, it is equilateral. If you see an equilateral triangle, it is also equiangular.